Okay, this is a lecture over three-way handshake. And as I said, the slides should be up there, and I did modify them today. So if you downloaded them before, I modified them like 30 minutes ago. Did y'all find those? So they're week 2? Okay. Yeah, actually, in case you can't find them, they are right in, hold on, here, right there, lecture 2, right there. Okay. One of the discussions we had with Dr. Schnoor, I think I might have mentioned this last week for those of us that were here, was you guys really need to understand networking, and I don't think everybody does. So hence I wanted to come up with this presentation. Made this Sunday. It's pretty detailed, and you have an assignment based on it. So let's go through this. Okay. Everybody know what a three-way handshake is? I'm assuming you've heard of it before. Yes? You've all heard of one, at least once or twice in our lives. Now, there's a file up there called 3-way demo, PCAP. So that's up there. I'm actually opening this with Wireshark. So as we go through this, these are the actual packets I used. Now, the frame numbers will be different because I went ahead and, when I made the PowerPoint, it actually included a whole bunch more than this. I just exported out just the packets in question for you guys to, easier for you to see. Okay? Now, a three-way handshake, as you'll remember, is SYN, SYNAC, and ACK. Okay? Easy enough? Everybody got that? Who sends the SYN?
The client.
Right. The client. So I'm going to be surfing a page on Google. So I send a SYN packet, which is basically a synchronization packet. So I send this packet to Google to initiate the communication. It's kind of like me calling Patrick here. I would call him. Okay? Then Patrick would answer the phone. Yeah, this is Patrick. And I want to talk to you too, basically, is what happens. So the server acknowledges the connection and then sends the synchronization packet as well. Okay? So in other words, telling me pretty much who he is. Okay? Then I reply back with the acknowledgement, and then we start communicating. Okay? That's all there is to it. It's pretty simple, but how does it actually work? Okay? Wireshark is nice enough to do all this for us. Do all of you, bring up that file I sent you all. Well, I put up there, the three-way demo. Do all of you showing the real sequence numbers and not the relative sequence numbers? So if you guys look at this packet, are you seeing these big long numbers over here? Yes, you are? Is everybody else seeing? Dawn, you seeing the big numbers?
I see those big numbers.
Okay, so for sequence, you see 850 something? Okay, good. If you guys don't, let me show you exactly where it's at in case someone on the recording doesn't know where to do it. If you go under Edit, Preferences, then go into Protocols, then under TCP, there's an option in here for, where is it? There's relative sequence numbers. Okay, I recommend turning that off. Because what happens is when you turn it on, what will happen is when there's a communication being started, it'll start at 0. Okay? Which makes it easy to follow, but that's not the real number. Okay? So that should be unchecked. Okay? Everybody understand why we're doing that? Patrick, you know why we're doing that? Heather, you know why we're doing that? Did you find that yet? Okay. And if you turn it off, if you uncheck it, you should actually see the real numbers. If you turn it on, watch what happens. My sequence numbers change to zeros. Everybody say that? When it's turned on, they turn to 0. And all that is, it's still a long number, but Wireshark says, I'm not going to confuse you with this big old number, so I'm going to go ahead and make it easy on you and change it to a 0. Which is okay, but if you really want to know how things work, that's worthless. You really need to see the numbers Because that's what's really happening. Okay? Heather, did you find that?
Working on it. I had to download the crap.
Oh. Well, that's right. You weren't here last week.
Yes, I was. I wasn't
Right.
here Tuesday.
Oh, okay. All right. So, now that you got that, hopefully, well, all but Heather, let's talk about this for a second. We got the frame and then the Ethernet. Now, let me show you a picture here. I'm going to try to find a picture real fast. Go TCP reference model. Hopefully I can find one pretty quickly. If I look at them here, you'll pretty much see, let me find, where's the one I want to see? Not sure, I'm not going to find the one I want. Well, that one's pretty good down here. Where'd it go? There it is. Okay. You'll see that, come on. Where'd it go? There it is. You'll see we have IP, then IP, either we have TCP or UDP. IP, is that the connection list or connection oriented? Anybody?
IP is neither. TCP is connection oriented and UDP is connection.
Right. That's what I meant. Sorry about that. Yeah, that's what I meant. TCP is connection oriented. UDP is not. IP runs under both of those. That's what I was trying to get to. Sorry about that. So you'll see we have IP and then TCP. If we had other packets, we could see IP and then UDP. Now, in our example here, if you actually expand IP, you'll see it's actually highlighting a specific portion of the packet. Okay. And if you click on the TCP, you'll see it highlights a different portion of the packet. And that's the different headers that pertain to the individual protocol. Okay. Now, back to my presentation that I so painstakingly made. Okay. Let's talk about this here for a second. Okay. So the first packet is the SYN packet. It says client selects a random sequence number, SEQ, sequence number. In this case, it happens to be 850.738.539. Sends that packet to the client, sends it to the server. So far, so good? Okay. Now, there are vulnerabilities in this, like known sequence number guessing attack. And actually, when I worked at a gym, that was one of the big issues was their system, their video recording system, had the vulnerability in it for a known, basically the sequence number could be guessed. And actually they wanted to pull their PCI compliance because of that. And I tried to, we finally got them to understand. I said that is on a video recording system. It has nothing to do with payments. It's on a totally separate computer system. It's just for the video. So even if they get into it, they're going to watch a video. They're not going to process a credit card. So there is a vulnerability in this. Okay. So we have a sequence number. Okay. That starts off as a random value, and the acknowledgement number starts off at 0. Okay. Hasn't gotten acknowledgement yet. Okay. We're going to get more into this. So far, so good. Heather, you with me now?
Yep.
Maybe? Okay. Now, this case, it says frame 50, but on your demo, it should be frame 0. Okay? So everybody see on the demo, it's actually frame 0. Okay? All right. Now, back to the presentation. Okay. Now, see, you like my little guy up there? SYN packet. He's like the devil. He's SYN. See? That took a lot of work. Okay. The next packet on the list, if we go back to our little demo here, you'll see the next packet has a SYN and an ACK. In other words, the server is acknowledging the SYN from the client, and then it sends its own SYN back. Okay? So now let's look at this more in detail. All right. So it's the server increments the client's sequence number and uses it as its own acknowledgement number. So the initial sequence number from the client ended in, where'd it go? 8539. So you see 8539 has been incremented by 1. So the server has taken the sequence number from the client, incremented by 1, and now is using that number for its own acknowledgement number. So you'll notice acknowledge is now ending in 8540. It's incremented by 1. So far, so good. And it generates its own sequence number. Easy enough to follow. Everybody get that? Patrick, you with me? So far, so good. Okay. So, now, and SYNAC, short for snack. So I bet your sandwich up there. So, come on, that took a lot of effort to find a picture for SYNAC. All right. The next packet. So the client sent a packet to the server. The server is now sent a packet to the client. Now the client has to acknowledge the SYN of the server. So it says the client acknowledge server's sequence number and uses it as its own acknowledgement number. In the same exact fashion as the server did it, it takes the sequence number from the server, which in this case ends in 9137, increments it by 1, and it becomes 9138. So far so good? Easy enough? Okay. So the server's prior acknowledgement also becomes the client's sequence number. Okay? So the acknowledgement from the server become the client's next sequence number. Let's look at that. That's where it's a little bit confusing. So okay, so we did the second packet. Now we're looking at the third packet. And if I expand out TCP, that's where you can actually see it. Now if you actually expand it out, you can actually go back and forth between them. You'll see on the second packet, the acknowledgement number ends in 8540. So then the next packet, which is now the client acknowledging the server, uses that same number, 8540. You'll see that it did not increment it. It used the same number. Easy enough? Okay. And then, now that's the whole three-way handshake. But from that point on, it actually uses that same number, but then starts incrementing it by the segment length. Okay, I don't have slides for this one, but if you look at between the third packet and the fourth packet, you'll see again the sequence number is the same. It hasn't changed. It's kind of like saying, hey, it's still me. I'm still, and the client, and just think about this for a second. So if someone is listening in on this network, detects a SYN and an ACK packet, they know it's in the middle of the three-way handshake. If they recorded the acknowledgement packet, okay, and the acknowledgement number, they know it becomes the next sequence number, okay? And they know the next packet, which is actually the one that's going to start doing something, is the same number. So think about it. If the communication's slow and they were able to capture that acknowledgement number, they could actually start sending traffic on your behalf because the sequence number hasn't changed. You'll see that? See, that could be an issue. So that's part of where it all comes in. So we send the get packet. Now, so that's packet 4. Now see packet 5, it actually changes a little bit. Okay? So packet 5, in this example, which I put up here for you, you should have seen some data. Okay? Does anyone know what the URL is based on this of what we should see? Anybody? Okay, does anyone know what the actual URL is by looking at this capture of where I should go to see this? We should be able to see it in this room. That's actually true. Okay, I'm going to go there. I'm going to go to, okay, I wanted to pick a very small one. So I'm going to go to, it's my.rose.edu/faculty/emoticons.jpg, I think. Okay, and that's what we get. Okay. It was basically the smallest picture I could find because I wanted it to be in an individual frame. So that being said, can someone tell me why, since that's what packet 4 is, Tony, it is Tony, isn't it? Make sure I get this right. Tony found that by looking at packet 4, and you can see that's a GET request. The GET request tells the server, hey, I want some data. So now one thing it's not showing, actually let me find it here real quick. You'll see it does still have some flags set. Actually has the acknowledgement and the push. Okay, it has them set. But so it sent a request out to get this packet from my.rose.edu. It wants to get faculty KDewey emoticon JPG. Why didn't we get it? Anybody? It was very tough for me to figure out why we didn't get it.
Didn't get what?
Why are we not seeing the data of that icon from the server? Because you think about it, packet 4 says, get it to me. And if you look at over on the left side, you'll see the source of packet 4 is my machine. The destination is the server. So packet 5, should that not include it? What do you think? Anybody got any idea why?
So you could have, if it didn't transfer via HTTP, it transferred at a different protocol, you wouldn't get it. You wouldn't have it necessarily in your capture. But this said do it by HTTP.
So normal HTTP traffic, it's nothing special. It's a regular JPEG on a website. It literally is nothing different. Tony might figure it out. Any idea, Patrick?
I'm trying to figure out why it says 304 not modified.
Well, you want a hint?
Sure.
It was cached in my system. Is that what Dawn thought?
Yeah, she said that.
It was cached. Because what I'd done was I had already seen it. Because me and Roy are looking at it, it's like, why didn't it transfer the packet? And we brought it up on his machine without ever going, and it transfers just fine. It's just that it was already cached. So, and now we did this also. I think this one was with Chrome. No, this was with IE. I used a couple different ones. But depending on your browser, you get different data back, which is different. Yes, Patrick?
So if your machine already knew it had the picture, why did it ask for the picture?
Well, okay, it sent it to it, and then it basically, I don't know, that's what took me forever. I'm like, there has to be something wrong with it, and we just did it on the machine. It worked fine.
Because your machine is asking the server to give it that picture.
Right. Yeah, you would think my machine wouldn't even ask the server.
Yeah.
All I know is it's the correct link. If you want to try it, don't go there. If you want to try it, here, you guys try this. Bring up your Wireshark, and bring up Wireshark and start capturing traffic. Oh, actually, don't start capturing traffic yet. But bring up your browser and type in this address. Is there a way to like zoom in like the screen or?
So the reason it did it is because your machine said, I have it,
Yeah.
but I'm going to check to see if it's been modified since I last got it.
Ah,
And
that's
that's
okay.
what the 304 is saying.
It hasn't
It's
been
not
modified.
So
Not-
it hasn't
there
been
you go.
modified, so use the image you have already.
So that's what the not modified error is. Okay. But go ahead and get this, you guys. Actually, let me try to get it myself too. I mean, it's tough when I first, it's like, what? Okay. I'm going to get, well, heck. I lost my thingy who's here. Oh, it's down here. Okay, I'm going to capture some data, and then I'm going to do a control F5. Should,
You used Chrome to pull that?
I did do it with Chrome?
Yes.
I couldn't remember, because I did one in IE, one in Chrome. Okay, there it is. And then, Yeah, then it actually transfers. So, yep, I got it just fine.
Yeah, you originally poured it on Sunday, 28 August
Yeah.
at 7:08 GMT, and it hadn't been modified since then.
Okay. All right. If you got now, see, I just did it again here, and you'll see there's my GET request. There's the actual segment of the packet. Let me zoom out. Now I'm gonna just move this over. Now, if you go down to TCP, you'll see obviously the sequence numbers and everything is the same, but the data of the packet, if you look down here, you can actually see it. And you can also do, where's it at? Follow TCP stream, and it actually shows you the GIF right there, the JFIF. And if you remember anything from the forensics class, if you change this to hex, down here where the packet starts, come on, well, basically right there. So FFD8, FFE0 is the actual packet starting, the actual graphic starting. Y'all remember that from forensics class? Obviously Don does. It's been years. But that's actually the file signature for a JPEG. Starts with FFD8, FFE0, then ends in FFD9 somewhere down wherever the packet ended. FFD9 right there. There's the ending of the packet right there. So we could actually extract this out and save it and have the JPEG as well. Okay, we can actually go. Actually, let's try this. If this works, it'll be amazing. FFD8, FFE0. It should go down to FF. Now we're too far. We got too much stuff. Hold on. Heck, we gotta find out where to go to. There it is. FFD9 right there. Okay, I did that. So I captured from FFD8, FFE0, and I'm. Actually, you know what? Hold on a minute. No. Let me find out exactly what that is. Maybe I'm confusing myself here. Let me get the actual. If you go to Gary Kessler, come on. Gary Kessler file signatures, and then we want to get a JPEG. FFD8, FFE0. Okay, I have the right one then. Okay. It just looks like I have too much. Okay, yeah. FFD8, FFE0, all the way down to FFD9. And I'm going to save as. Hopefully it only gets the data. No, it got all of it. Darn it. I only want that one bit. FFD8, FFE0. FFD9. Well, I don't know why this won't let me just do part of it. Copy. Okay, do we have a hex editor on these? File new. Paste this in. What? Pasting this. We can't paste? Paste insert. Move to the text. What the? Well, it's not wanting me to do this. Oh, because it got all the rest of it as well. Well, heck. Alright, I'm not going to try to paste this anymore. Because it got all the other formatting, which I don't particularly want. Alright, so let's go back to where we are, because you need to know more before you can complete this project. Okay. Close this one out. That's what we want. Is that? No, that's not it. Okay, everybody okay on what that did? How that worked? So far, so yes, maybe somewhat at least. Okay, so, and there's where it got the file. So now the actual transfer of the data. Now, if you look in here, I'm at the packet 53, which is the next packet. It actually shows the known sequence number. Okay? Y'all see that in Wireshark? Do you got the old Wireshark up there, Tony, or the new one?
I'm using the new one.
Are you starting to like the new one?
No.
No. I'm wondering, does the old one show next sequence number? I can't remember if it did or not.
I don't recall it doing.
Yeah, let me zoom out here if I can find out how to zoom out. See on the left side here where it says known sequence number? Yeah, I don't know if it shows that one or not. Well, the way it gets the known sequence number is it takes the sequence number, adds the segment length to it, and that becomes the next sequence number. Everybody see that? So it took the sequence number, adds the segment length, and that becomes the next. So if we actually look at the next packet, so remember it should end in 9300, it actually shows the acknowledgement is for 9300. So it actually does. Okay? Easy enough? Somewhat? Did anyone follow that? I know Tony did. Don's like, no. Patrick, you kind of follow that? Okay. It's not hard, but there's a lot more involved in a three-way handshake than we originally thought. Okay? Now, we're not done yet. Okay. So the actual data from the client to the server would obviously, the acknowledgement will be the prior one plus the length and so on and so forth, and that's how we get the next one. And 55, or the last packet on your list, is the acknowledgement, again, would be the prior sequence plus the length. All right. Now, we need to talk on how this thing works. Now, I actually made a little table here showing the sequence numbers. Okay, so you see the first packet, again, yours started at 0 instead of 50, but we had the sequence number. Where'd the initial one, where'd this one up here come from? Anybody but Tony?
The initial, that's us sending it out.
That's the client sending it out, but how did it come up with that number? Anybody? Right, it's a random 32-bit number, exactly. So it came up with a random number, sets acknowledgement to 0. Then the server back to the client is that sequence number plus 1. Then it comes up with a random sequence number for itself. Then you notice the acknowledgement from the client back to the server is that number plus 1. All right. And then the sequence number from the client is the same one. Because remember, it's its next packet anyway. Yes?
So essentially, they just constantly flip back and forth, and during the three-way handshake, they increment by 1, but after that, they increment by adding the
Segment length.
segment.
Exactly.
And that's it.
Yeah. Pretty much it. I mean, simple, isn't it? I, never looked that way. Okay. So you notice now that one's copied down. Okay. That's copied down. Then we start incrementing by the segment length. Remember, this segment length was 760. So we add 760 to that. So what's happening is the client is giving a sequence number plus the length. The server is saying, okay, I received your sequence number plus your packet was so big, adds them together, and that becomes the acknowledgement number. Then that number gets sent to the client, which then uses it as the next sequence number. So that's how they can put the packets in the exact order they go.
Relying on this for any sort of security application is kind of stupid.
Probably one of the reasons the IP4 is gone. Well, it's here, but it's gone. You all know that. It's not being used anymore. It's used internally, but there's really no new numbers to give out. So everybody see how that works? Pretty simple. Now, there's not a lot of being data transfer on it, so I'll do that one again another day, but that's why you don't see a whole bunch more. But a little more intuitive now. All right. Now we get to the fun stuff. The TCP header. Now, this is what it looks like. So if I go back to my traffic capture here, and if I was to pick a packet, we'll pick this first one, it's fine. And if I was to just click on TCP header on the transmission control protocol, you'll see it highlights certain sections at the bottom. Everybody see that? It highlights a specific piece at the bottom. Now, if you look at that piece, the first 16 bits is what? The source port. The second one's the destination. So if I open this up, you'll see the source port is those two. Destination is those two. Now, that brings up a problem. So the source port is C8D6. That's what it shows right there. So if that's true, then why is it saying 51414 up here?
Because one's in decimal and the other's in hex.
Exactly. It's giving it to us in a format that's easier for us to understand. So if I was to go into hex and typed in, was it C8D6? C8D6, convert that to decimal, I get 51414. Okay? So then the destination port. So if I was to put in the destination port of 80 in decimal, convert it back to hex, I get 50. And we know that the destination port takes up those 2 bytes down there, 2 8-bits and 16-bit. So 0050. Okay? Don't make the mistake if it's port 50. I'm telling you, a lot of people do. See, it's easy to understand this one. So why do you think it's easier for people to convert that one than the next one? It doesn't look like a number. People look at the C8D6 and like, oh, that's obviously hex. It needs to be converted. So many times people look at the 0050 and put down 50. I mean, it happens all the time. But the 50 is a hexadecimal 50, which then converted to decimal becomes 80. Easy enough? You're going to have to do this, by the way. Okay. You're like, what? Okay. So, there's our ports. Then we have our sequence number. So our sequence number is 32. Where'd my calculator go? There it is. So 32. We go back to hex. 32 B5. No. Where'd it go? 32 B5. 3D 6B. 6B. Y'all see that? Okay, you guys should have the same one on yours. Convert that to decimal, and it should come out to 850,738,539, which it does. Okay, that's why I don't like everyone to use the relative numbers, because if you convert that, I literally have students who tell me it's 0. The sequence number is not 0. It's 850,738,539. The 0 is just a relative that Wireshark does for us. So far, so good. Okay. Now the acknowledgement number is a 0. So why is the acknowledgement number 00000000 and not just 0?
Because you have to fill in those specific bit fields to maintain your alignment for the
Right.
header.
Because if we look up here, you'll see the acknowledgement number is actually how big? 32-bit. Since it's 32-bit, we actually need to use up 32 bits for the 0, because we know in just a second the acknowledgement number becomes, where'd it go? 7, no, I'm sorry. The 850 gets copied into the acknowledgement number. Is everybody seeing that? Everybody know how to track that? Okay. So then, this next part, the header length is actually right there. Here's another one that gets people all the time. Header length is 32. Is that correct? It's 32 in hex. Again, if I go hex 32, convert the decimal, I get 50. No, wait a minute. Is it 50?
Oh, 32 is 50. This one's 34.
So, why is it not showing me the right thing here? Okay, we got to figure out why. Hold on. We got to figure out why. Flags is actually that entire thing. Oh, because it's a portion of it. That's why. We're going to get that one in a minute then. I want to look at the flags. Expand your flags. So, flags is 80/20. Everybody see that? Not 80/20. Yeah, 80/20. So when I select flags up here, I get 8002. Everybody see that at the bottom? 8002 in hex. Then why does this say flags is just 002?
Because part of that first byte is actually also something else.
Right, exactly. The part of the first byte, if we look, the first 4 is actually data offset. Then we have reserved, 4 more for reserved. So flags ends up being how long? 1, 2, 3, 4, 5, 6, 7, 8. Flags is actually 8. Now there are different versions, and depending on the packet, they actually could be slightly different. But this is the one that's correct for these. So if they're 8, so when I look here in fin, SYN, reset, push, there's 4. Acknowledgement, urgent, echo, and congestion's 8. Everybody see that? So how many bits are our flags supposed to be? How many bits are our flags be? Just 8, exactly. The knots is not part of the flags, and neither is the reserved. Okay?
So why do they include that under the flag terminology?
Because it's different. Sometimes they actually even have different ones in there. I just don't have an example to show you. Yeah, because, I mean, if you look under, let me find an example for you here. Let me go here, and I'm going to put in TCP Header and show images. So let's look at this one. So that one is only 1, 2, 3, 4, 5, 6. So it really depends on what it is. It's not always the same.
Depends on the person's definition of flag.
Well, kind of, yes, kind of. But for yours, it's 8. Just remember that. It's 8. So our flags on, what packet are we on? We'll go back to the first packet. Our flags are 2. 002 in hex. So why do I have 10 down here? So if they're actually 2, why is it giving me 10?
Because down there it's binary.
It's binary. 2 in decimal is 10 in binary. Okay? So first are good? Everybody somewhat with me? Okay. Alright. Now, let's go, where was I at? We really don't need the rest of those, so let's look at this next slide. I lost my slide. Okay, so this is the one you should be using. Again, the other stuff's important, we just don't need it for this. Okay, so here's our flags. So in this example, we have a 10. Okay, so let's look at calculator here. And under binary, I'm going to put in 1, 0, actually I'm going to do this. 1, 2, 3, 4, 0, 0, 0, 1, 0, 0, 0, 0. Did I need to put the zeros at the beginning? I typed them, but they disappeared. You all agree with that? Okay, you don't need to put them in, because anything to the left of the 1 disappears. It's kind of like if I was going to give you $10, that would be 10, but 0, 1, 0 is still 10. You know, it's not needed. Okay, so there's our flags. Okay, if I convert that to decimal, why did I get 16? Yeah, why did I get 16? That's weird. In binary, I have 4 zeros. All right, let me find this packet. Find out what's going on. Which one is that? Anyone know what packet that is? Is this packet here? So the flags is 5010. So 10 in hex. Oh, I was going to decimal. That's why I was an idiot. Okay, it's hex to binary, not decimal. Yes.
So when you ask us, like in a quiz, for example, to return the contents of a field of a packet header, do you want when do you want the leading zeros and when do you not? Because I know that
Only on specific times, especially like when it's the ECN, where it specifically is returning all bits, and it'll actually tell you in here. Let me see if I can find that. I know exactly what you're talking about, that other quiz in the other class. Okay. Normally a flag is on or off, so it's just a 1 or a 0. If I'm asking you for a specific flag, like the SYN flag, it's 1 or a 0. If I ask you for all the flags, you could list, I would list all 8 of them. Okay? But let me find the one you're talking about. Let me see an example of it. It's under...
which one specifically we were talking about in that other class, but it wasn't the one of the 0 ones. It was like, there was this field we wanted it returned as a number, and this field we wanted it returned as a set of bits.
Yeah, I'm trying to remember what that was. It obviously wasn't an HTTP packet. I can't remember what it was. Yeah, I can't remember what that was. Oh, here it is. The differential service field. Okay. And the ECN. Okay.
Yeah. So I was just returning that as 0. What other
Right.
number was it?
Because if I remember right, the DSC is actually all 6 bits. And I think I wanted all 6 so you realize it's not, so it is actually taking up the 6 bits. Whereas the flags are only taking up 1 bit. Okay? See, DCN, that number takes up 6 bits. Flag only takes up 1.
The reason I was showing it as just 1 digit was because it says default 0, and I figured it just wants it can be returned as a number.
Yeah, but the problem is with that, how do I know you didn't think it was just a single 0? Yeah, because if you actually look it up, it actually says it is specified in 6 bits. So that's why I did that, just so you know it was 6 bits. Okay, I remember what you're talking about now. Okay, let's continue on. So everybody okay on how we got the flags there? Now let's talk about how to read the hex. We kind of already covered this. So, so the Ethernet frame shows us our MAC address as the first 2. I'm going to actually bring one up to show you. So I'm going to go to this one right here. If I click on Ethernet, you'll see it's actually, let me get it so I can see it on the screen. So let's do this. You'll see the Ethernet is that first section, all the way through the type. So if I click on Ethernet right here, you can see it's giving me, it's hard to see, the destination, and then source, okay, and then the type. That's all I get out of Ethernet. Then IP is actually giving me the next section, which is right there. I'm trying to keep all this on the screen at the same time. There's the IP. Oh, I can't get it all on the same screen. Okay, there's IP. You'll see it actually starts. Well, heck, I moved it. Starts over at the right, gets the entire second line, and gets the 2 on the left. So even though it's an IP header, someone last semester or something was trying to think that, it's kind of separate. It's actually just a continuation of the Ethernet. Then you get IP, and it's kind of all added together. Okay. Oh, I meant to pull the. Oh well, I didn't set the locks right. Sorry. And then the next part, the TCP portion, is actually that next section, where you can see the sequence number, the acknowledgement number, and the flags. Okay. So easy enough to follow. Yes, sir.
Just randomly curious. Is there any particular reason that MAC addresses do it backwards and everything else and have the destination first?
I don't know.
Like, does it maybe make it like less overhead?
It was an efficiency thing, so that it had to read the destination and could make a decision on whether this is relevant.
That makes sense.
For broadcast and stuff.
So I guess at like really high throughputs, it can make a big difference only having to read the first little bit instead of.
Think about when this was written out.
True.
DARPA did this back in the 60s.
And-
Not DARPA. Xerox and them did this back in the 60s.
And it's kind of a somewhat example of what he just said in our vSphere system down there. What we did was when we created our ACL, which is basically our firewall, our access control list, we looked to see what the most traffic was coming. made sure we were checking that first, especially if we're going to allow something through. You know, we want that at the beginning and the stuff that wasn't used much at the end. Okay, so everybody's with me so far? So the sequence number is actually 32B53D6B, which turns into that. The acknowledgement number is all zeros. The flags 8002 is all that, but they're not all the flags. Okay, it's just those 8. Okay, so if you convert the 8002, you actually get that, but it's actually that. Everybody okay? You got that? You should be able to solve your homework. Now, back to the flag one more time. Here's where I'm showing exactly where they're at. Okay. Now, I want to go to here. Do you think, looking at, I'm referring to only the first 3 packets on this list. If you were to get just those 3 packets without Wireshark, could you put them in order? You should. You should be able to calculate what the sequence number is, what the acknowledgement number is. Now you should know enough to be able to determine which one goes in what order without using Wireshark. Y'all agree? John's like, sure you can. But just because I'm so nice, I made, well, where's my other file? Did I close D2L? Hold on. I think I closed D2L. There it is. Okay. We got another project. And here's your project. I want you to gain an understanding of TCP headers and 3-way handshake. Analyze the 3 packets below and answer the questions in the quizzes section. The packets have been labeled as yellow, orange, and red. That's all you need. The questions are, what's the IP address of the client? Okay. What's the IP address of the server? Think we can figure that one out? I'm not even color code exactly where that comes from. What order do they go in? And I did make sure that there's every possible combination there. So, what's the initial sequence number granted by the client? What's the initial sequence number generated by the server? And the final sequence number of this handshake, and the final acknowledgement number. And then, what is the value of the flags in the yellow packet, the value of the flags in the red packet, and the value of the flags in the orange packet. In binary, showing the correct number of bits.
Do you want the value of the flags, or do you want the full
I want the value.
16 bits?
I want just the 8 bits.
Okay.
So if it's, just, what is it, hold on, what's the one at the end? What's the one at the end? So if it's just the SYN packet, it's going to be 0000010. Okay? Everybody got that?
You want it in binary and not
In binary. I want it in binary.
Okay.
Okay? So, it's not that tough of an assignment, but I'm hoping by doing this assignment, you'll understand how to convert hex to decimal or binary, and what parts of a packet actually become what. Oh, lost my thing again. And there's your 3 packets. Okay? They are not in the correct order right now, I'll tell you right now. Yeah. Okay? Did you already solve it all?
I have not solved it all, but I knew that just by looking at
Okay.
well, I won't say anything. But it was very easy to tell they were not in the right order.
Right. And I was nice enough to put them in as an image so you can't just paste them and then import them into Wireshark. And you can do that, by the way, but don't. Just do the conversions. Don't just type it in and convert. No, you need to be able to follow this. So, everybody okay on what you got to do? Okay. Did I put a due date for this thing in here?
I think you did the 15th.
Okay. Yeah, I think I gave you a little more time on that. Now, that being said, let me bring up my calendar here real quick. Next week, Monday's a holiday. Doesn't affect this class. I'll be here next week, but the following week, the 15th, I'll be in Boston. I'll be there, although I'll be there from the 14th to the 16th, so this class. So we're not going to meet. I'll have something up there for you, but We're not going to meet on the 15th.
You mean you're not gonna have Roy teach this class?
No.
That would be interesting.
Is everybody okay on that? The 15th, which is 2 weeks from now, I will not be here. This means, Heather, you cannot come and ask me questions on other classes either.
Hey, your name's on the original assignment.
Yes. All right, that's the end of this one.